Okay. So yesterday we saw how to solve differential equations using Laplace transforms. So someone asked me, can we use Laplace transform to solve PDEs, linear partial differential equations? So let me give a couple of examples how to do this. So application. To solve linear partial differential equations. Okay. So let's start with this example. Del u by del t is del 2u over del x2. Okay. Conditions are u, x. So let me write y. Y x0 is a function of x. It's given by 3 sine pi x, 2 pi x. 2 pi x. Y 0t equals 0, y 1t equals 0. So the range of x and y is 0 less than x less than 1, t is positive. So these are the conditions. Okay. So we can think, so y is a function of x and t. Okay. So what we can do is apply the Laplace transform only for the t variable. Okay. Using the same formula, but just using the Laplace transform formula for the t variable. So let me write ys, which is the Laplace transform of xt. Okay. And for this purpose, we think of x as fixed. Okay. So sometimes it's prudent to incorporate the notation in the notation t here as well, so that we can remember that this is for the t variable. What will you get? Okay. So first one is just the differential. Yeah. So s yts minus y of x0, isn't it? Right? And then what is this? This is just the d2 over dx2 of ytx s. So remember that yts is also a function of x. Okay? Because we did not do the Laplace transform on the x variable. So it's the x is still inside this function. So we can differentiate it with respect to x. So there are no derivatives in terms of t. So we can think of it as an ordinary differential equation. Okay? Now we know what is yx0. It's given from the condition. So syts minus 3 sine 2 pi x is d2y ts over dx2. So we use the method of an integrating factor. Okay. So we can write it as d2 yts by dx2 minus s yts equals minus 3 sine 2 pi x Okay. So let me just write down the. So we can solve it. Okay. This is a linear ODE. So you can solve it using many methods. So the answer, I'll just write down the answer to save time. C e to the minus root s plus C2 plus root s. Huh? Ah, yes. 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 Thank you. Yes. Plus, what is it? I forgot. So the answer is 3 over s square plus 4 pi square sine of 2 pi x. So now we need to solve for C1 and C2 using these boundary conditions. Yeah. So if we put x equals 0, this is 1, this is 1, and this is 0. Okay. So you get C1 plus C2 equals 0. Yeah. So this is, yeah. So this is actually the inverse Laplace transform. No, maybe. I made a mistake. Wait. X square plus? No, it's not s square actually, it's just s. Maybe I made a mistake. Well, what one can use here is, so if you just take the Laplace transform of this, so you get yts, okay? But yts is equal to 0 to infinity e to the minus st y x s dt. Yxt dt. You agree? But if you put x equals 0, then this is 0. So y of ts at x equals 0 is 0. Similarly, y of ts at x equals 1 is also 0. Okay? So it really depends on the values of small y. So yeah, so this is correct. Okay? The other condition you get is at x equals 1. So you get C1 e to the minus root s plus C2 e to the plus root s equals 0. And if you solve these two equations, you will get C1 and C2 are both 0. Okay, so the solution is, so yeah, this is not the inverse. Yeah, so y is 3 by s plus 4 pi square sine 2 pi x. So if you take the inverse Laplace transform, so there is you only have to take the inverse for the s variable. So you get e to the minus 4 pi square, isn't it? It's just 1 over s translated by 4 pi square t sine 2 pi x. Okay, it's clear? Okay. So this is your solution. So you can cross check by putting it and checking that this is in fact a solution. So another problem. So do you know what this equation is called? One-dimensional heat equation. So it gives you, so suppose you have a table, let's say, and you have a heat source here, okay? So this starting temperature, let's say, is 0, but you start heating it and you want to find out what will be the temperatures at an arbitrary point, okay, as time increases. Okay, this is governed by the heat equation. Very good. So another example. This is 1. This is 2. Del y over del x equals 2 del y over del t plus y. So conditions are y x0 equals 6 e to the minus 3x and y xt is bounded for t greater than 0, x greater than 0. So in many physical systems, you want your solutions to be bounded, otherwise it will not make physical sense. So this is a natural condition to put. So we do the same process again. We apply the Laplace transform with the t variable. Okay. So the first one is just d over dx yts. Okay. The second one is 2s yts minus yx0. This one. Yeah? 6 e to the minus 3x plus yts. Okay. So this is d by dx of yts minus 2s plus 1 yts. This is equal to minus 12 e to the minus 3x. Now you can use again the method of integrating factor. You can write this as yts exponential integral 2s plus 1 dx. So if you differentiate this, you will find that you will get such a term, but there will be an additional e to the minus integral of this on the left. So you have to multiply it again on the right. So what do we get? So d over dx yts, and this is just e to the minus 2s plus 1x. This is equal to minus 12 e to the minus 2s plus 4x. Yeah, this is correct. So you can integrate yts e to the minus 2s plus 1x. This is equal to this 6 over s plus 2 e to the minus 2s plus 4 x plus c. This is the answer. So, you can argue, since yxt is bounded, okay, then you will get in the end that c is equal to 0, since yxt is bounded. I'm not giving the details. Yeah, I mean, this is, you can just prove it yourself. Okay. Just check that you will get c equals 0 when yxt is bounded just by using the formula for the Laplace transform. Okay. Okay. So you get yts equals 6 by s plus 2 e to the minus 3x. Am I correct? Yes. So the inverse Laplace transform, this is your solution yxt equals 6 e to the minus 2t e to the minus 3x. Okay. You can either use the integral for Laplace transform to conclude that c equals 0, or you can just take the inverse Laplace transform for the entire thing and then use that yxt will be bounded, so then you will get c equals 0. Okay. So as you can see, there is not much difference for partial differential equations, except that you will get another sort of an ordinary differential equations in the other variable, which you have to solve, right? Okay. So this is for partial differential equations. Other problems that can be solved using Laplace transforms. So let me talk about integral equations. So especially integral equations of Volterra type are susceptible for use of Laplace transform. So what are integral equations? So you can have ft equals integral 0 to t k u t tu y of u du. Here f of t is known and one wants to solve for y. You want to find the function y, for which, for a known function, this k is also known, f is also known, and you want to find the function y for which this equation is satisfied. This is called yes, Volterra equation of the first kind. So when I say Volterra equation of the first kind, this gives you a hint that there will be a Volterra equation of the second kind, right? So if you have yt equals ft plus lambda 0 to t k t u yu du. So you see that the unknown y is both inside the integral and also outside. F and k are known. So this is the Volterra equation of the second kind. And one can immediately see that these problems, if, for example, if these integral kernels, if you remember from the first class, these are called integral kernels. If your integral kernels are nice enough, then you can use Laplace transform techniques, because you know what is the Laplace transform when you integrate from 0 to t. For example, if ktu is of the form kt minus u, right? If ktu is of this form for some function small k, then what will it be? This will be a convolution equation, and you know how to solve for convolution equations using Laplace transforms. So one property will be for the integral, one for the, so it's just a convolution, so you know it will just be the product of the Laplace transforms of small k and y. Okay, so let me give you an example. This is a classical example. By classical, I mean it's almost 400 years old. Okay. Anyone? What is it called? It's called the Crone problem. Crone problem. Have you heard about this? Crone problem? Huh? Say it again. Yes, something to do with time, because you have Krone. So this is a Greek word. Toto means same. Krone means time. Okay, chronos means time. So equal time is also called the isochrone problem. Iso means equal, toto means same. So what is this problem? So suppose you have a curve on the plane, Euclidean plane, okay? And suppose you have a bead. So suppose this is like a wire, and a bead is attached to the wire, okay? So let's call this point UV. And there is a uniform gravitational field on this plane. So if you release this bead, it will fall down along the wire, okay? So this will fall down along the wire towards the origin, right? So the Crone problem asks what will be the shape of the wire, so the equation of the curve, such that the time that the bead takes to go from the initial point to the rest point, to the origin, is independent of the starting point. Okay? That's why it's called equal time problem. So equal time means, so suppose that this takes time. So suppose time taken by the bead to go from P to O, so O is the origin, is tau P. So tau depends on the point from where you release this bead along when it goes down under gravitational force. Okay. Suppose Q x y is another point on the curve. Okay. So what will be the time taken for the bead to go from Q to O? It's just tau of Q in this notation, the time taken by the bead to come from Q to O is tau Q. The time taken by the bead to come from P to O is tau P. Okay. So when the problem is to find the equation of the curve such that tau Q equals tau P for any 2 points P and Q on the curve. So find the equation, so this is the problem. Find the equation of the curve such that you have this property. Okay, you have the same time independent of where you start your bead. Okay, so you'll find that you'll end up with an Volterra equation, okay, to solve this problem. So let's see. So this problem was posed by Huygens. Have you heard about Huygens? He was a physicist. Christian Huygens. Yes, he's a Dutch physicist. And he posed this problem in the 17th century. Okay? And it was solved by many people. But the solution given by Abel, Niels Henrik Abel, is also one of the greatest mathematicians of his time. He gave a solution which uses the integral equation and the Laplace transform technique to solve this problem. So let's see what is Abel's solution. Abel's solution. So suppose your so let's say the mass of the bead is m. Okay, mass is m. Okay, and starting from O, the distance along the curve is given by sigma. Okay, so sigma is the distance along the curve. Okay, so we use law of conservation of energy. Okay, so suppose that Q, the bead is released at Q with rest velocity. There is no initial velocity. So then kinetic energy at Q plus potential energy at P is at Q is equal to kinetic energy at P plus potential energy at P. So this is the law of conservation of energy. What is the kinetic energy at Q? It is released with a rest velocity, so it's 0. So this is 0 plus, what is the potential energy? It's mg y. The height is y. This is the height from the ground. What is the kinetic energy at P? No. So when you are dropping a bead, it will have some velocity here, right? The velocity is given by half mv square, isn't it? Sorry, the energy is given by half mv square. M v square, v at p, plus mg v. So v, so let me use another notation. X, y, S, T, let's say. Okay. So this is mg t. Now, what is Vp? Vp is the derivative of the arc length, isn't it? So this is half m d sigma by dt dy square plus m dt. Sorry, no, let me check. A little bit confused. So this is not the. So this is the time. So I'm messing up with the notation. So we call this y prime. This is x prime, y prime. And this is the time derivative of the arc length. Will give you the instantaneous velocity of the particle of the bead. So in the end, you get a differential equation. So you get half m d sigma over dt whole squared equals mg y minus y prime. Okay? So d sigma over dt equals, so m cancels out, 2g y minus y prime, square root of this, and you have to put a plus minus sign. But since this is a physical system, you can see that when time increases, sigma will decrease. So sigma is the arc length from here to here, right? And you're releasing the bead from up there. So when time increases, it falls along the bead. So the distance from the origin will decrease. So along the arc length will decrease. So in fact, d sigma by dt is negative. Okay? Okay. So what one can do here is take minus dt on one side and 1 over root 2g y minus y prime d sigma on the other side. Okay. Now suppose that the arc length sigma is given by a function of y only the second variable y. Okay. Then I should say y prime here. Then d sigma is some function f of y prime dy prime. So this is just, f is just g prime, right? So we substitute it here. substitute. So you get minus dt equals f of y prime over 2g y minus y prime dy prime. So time starts from 0 to t. So if you integrate from 0 to t dt, this is integral. You're starting from y and ending in y prime. Okay, f of y prime over root 2 g y minus y prime dy prime. Okay, so this means so this is minus t, and on the right hand side, so this is integral y to y prime fy prime dy prime over root 2g y minus y prime. Okay. Sorry, I should be getting 0 to y prime. Okay. So let's integrate it from 0 to tau q. Okay. So I integrated from 0 time to the time it takes to land up at the origin. Okay. So at time 0, it is at y prime. Sorry, it is at y, and at time tq, it will be at 0. Okay. So this is 0. It's minus tau q. So this means that tau q is 0 to y fy prime over root of 2g y minus y prime dy prime. Okay. So this time, you want it to be constant, independent of y, isn't it? You're starting from a height y, but you want it to be independent of y. So this is some constant, let's say t naught, okay, which is independent of y. So it's a constant. Is this an integral equation? This thing. So you can write it as follows. So I put it in a way which is easier to see. You can just put y prime to be u. This part is known. You have to find out fy, okay, and this is a convolution. This is the kernel, 1 over 2g k of y u. This is 1 over 2g y minus u. Is this a convolution equation? You only have y minus u term, okay? So you can put it as some function of y minus u. So this is in fact a convolution with small k and f, okay, and this is a constant. So this is the Volterra equation of the first kind, and in fact it's called a Abel's integral equation. So this is called this equation T naught equals integral 0 to y fy over 2g y minus u, sorry, fu du. This is called Abel's integral equation. Okay, and we can solve it easily. Just apply Laplace transform on both sides. On the left hand side you will get T naught over s. On the right hand side it's just the product of the Laplace transform of f and of this guy here. Okay, so this is Laplace transform of f u or t multiplied by the Laplace transform of 1 over root 2g t, right? I'm going a bit fast here because I don't have a lot of time, but if you check these steps you'll find that it's just the product of these two. So this is, let me write it, f of s. This is 1 over root 2g. Do you know what is the Laplace transform of 1 over root t? This is gamma half over root s. Okay, gamma half is root pi. So fs is equal to T naught root 2g root s over s. So this is 1 over root s. Okay, so now apply again, sorry, there is a 1 over root pi. So if you apply the inverse Laplace transform, this will give you T naught square root 2g over root pi, and again you get the same. So it's just Laplace inverse of 1 over root s is just 1 over root pi 1 over root t. So this is 1 over root pi root t. So this is T naught 2g over pi 1 over root t, and this is your f of t. Okay. Now this is not the equation we want because this is derivative. So in fact this is again a differential equation. Okay, and this equation is just dg by dy or dt, I think, is t0 some constant over root t, if I am correct. Yes, and in fact this differential equation is well known, and it gives you the cycloid. The solution to this differential equation is something like this. So, okay. Okay, this is the inverted cycloid actually. So when your bead has this cycloid form, it doesn't matter from where you start your bead. Okay, it will always take the same amount of time to get to the origin. Okay, why is this useful? This was useful for Christian Huygens to design clocks. Okay? He wanted the pendulum clocks not to depend on the starting point. It should always take the same time. Okay? So to have reliable clocks, that was his motivation to pose this tautochrone problem. And there is a related problem called the brachistone problem, brachistochrone. So brachistos means shortest, the shortest time, and in fact the answer is the same. Okay, the answer to the tautochrone problem and the brachistone problem is just the cycloid. Okay, this led to a lot of development in physics, especially in optics and in mathematics. The calculus of variations all have the history can be traced to the solution of the tautochrone problem. Okay, so it was a very important step in the development of calculus. Okay, so I have 10 minutes, only 10 minutes. So let me give an example of an integral differential equation. And I hope you will look it up when you go home. This is very important in engineering. This is called a PID controller. Okay, so P stands for proportional, I stands for integral, and D stands for derivative or differential, what you want. So proportional integral derivative controller. This type of controller is used, for example, when you are on a flight. Sometimes the pilots use the autopilot mode, right? To fly the plane, they just leave it on the computer. But if you're just leaving to the computer, you should have the right algorithm so that the flight doesn't crash, right? That would be disastrous. So PID controllers are very useful whenever you want the control to be given to the computer, okay? And the computer runs whatever system you have. For example, if you can also do this for cars, ships, right? And this is used in many other places as well. PID controllers are very, very useful. What is the equation? I just give the equation, okay? This is ut equals k0 yt plus integral 0 to t yu du plus, so this is k1, k3 dy by dt. So this equation has integral and also the derivative. That's why it's called an integral differential equation. And as you can see, this is very much susceptible to Laplace transforms because you have a 0 to t integral. And in fact, all of the analysis of PID controllers rests on Laplace transforms. Okay? So the next time you're flying on a plane, you can thank the Laplace transform for being safe. Okay? So people who ask, for example, why do you do mathematics? Why is it useful? So you can tell them that it's useful, it's everywhere. Okay? You don't see it even when you're using your phone, even when you're using your computer, when you're driving a car, flying on a plane, it's everywhere. Okay? You cannot escape from it. So please look it up. Please learn why is it useful, how it is solved. So Laplace transformation gives you the conditions for the stability of the system. Okay? And like I said, the whole analysis of PID controllers rests on Laplace transform techniques. So this is a very quick example of a very useful tool, which is used in engineering everywhere, where the Laplace transform is crucial. Okay? Now lastly, in 5 minutes, I'm going to give another example where Laplace transform techniques are useful. This is for the recurrence relations. So what are recurrence relations? These are relations of the type. So suppose that an is a sequence of numbers that satisfy some equation like this. Okay, alpha and beta are also constants with some initial conditions. Let's say A0 is 0, A1 is 1. So you want to solve for an. What is the value of an in terms of n only, such that this equation is satisfied. So this is called a recurrence relation. A very very famous recurrence relation is when an plus 2 equals an plus 1 plus an. Do you know what is this? Huh? Fibonacci series. Yes. So here alpha is 1, beta equals minus 1. Okay? So let's try to solve this equation. So what is the idea here? I define a function ft on the positive real line, okay, as follows. So ft is just an for n less than equal t less than n plus 1. So what does this function look like? So this is 0, then 1, then 2, then 3, and so on. Oh, I'm sorry. So it's just an. It may not be 1, 2, 3, 4, but it's an. Whatever the value of an is, it will take. So if an is 1, 2, 3, 4, n, then it will just be something like this. So I define this function. This is a piecewise continuous function. Okay. Now, so I write it in terms of ft plus 2 minus alpha ft plus 1 plus beta ft equals 0. So let's take the Laplace transform of f of t plus 2. Can we compute the Laplace transform? 0 to infinity e to the minus st f t plus 2 dt. So just make a change of variables. What will you get? You get 2 to infinity e to the minus s u plus minus 2 f of u du. Okay, so I just put u equals t plus 2. Okay, so e to the this is just t is, yeah, so e to the 2s f of, no, the range of integration has changed, so you have to compensate. So you have to write 0 to infinity e to the minus su fu du. Okay, so you have to compensate for the part from 0 to 2. So from 0 to 1 ft e to the minus su, in 0 between this interval ft is what? A of 0. No, I will add again from 1 to 2 because it's different from 0 to 1 and 1 to 2. So you will have two integrals. But the first one is 0 because A0 is 0. So there will be into 0. There will be another integral from 1 to 2 e to the minus su, and the value of ft in this interval is a1, which is 1. Okay. So you get e to the 2s. This is just the Laplace transform, fs. And here you get e to the minus u over minus s from 1 to 2. So this is e to the 2s fs minus, so you can just write plus 1 by s e to the minus 2s minus e to the minus s. Okay? So this is your Laplace transform for f of t plus 2. Similarly, you can write the Laplace transform of f of t plus 1, and this is just e to the s fs minus a0 e to the s 1 minus e to the minus s over s. But a0 is 0, okay? So this is just 0. So please check that this is true. So what will you get when you apply the Laplace transform from this equation? You will get e to the 2s fs minus e to the s 1 minus e to the s minus s over s. Okay, minus alpha e to the s fs plus beta fs equals 0. Okay, then the solution I just write down directly. Solution is e to the s 1 minus e to the minus s by s times 1 over e to the 2s minus e to the alpha e to the s plus beta. So now this is a quadratic equation in e to the power s. So you can solve it, and you can write this in terms of its roots and use partial fractions to expand. So you will have something like this, 1 minus e to the s minus c1 plus b e to the s minus c2, where c1 and c2 are roots of this equation. Okay, and then I have used partial fraction expansion to separate them in two things. So in the end, you will have, one has to take the inverse Laplace transform of this kind of function. So one has to take the inverse Laplace transform of e to the s 1 minus e to the minus s by s times 1 minus c e to the minus s. Okay? So this is just so both these terms are of this type. Okay? So here I am going to cheat a little bit, and I'll just tell you what is the answer. Okay? So this is just c to the power n. Okay? So this is, so let me write it like this. This is g of t, where g of t equals c to the power n for n less than equal to t less than n plus 1. Okay? So when you take the inverse Laplace transform there, you will get the solution f of t this will be A. First one is C1 to the power n minus B or plus B C2 to the power n for n less than equal to t less than n plus 1. Do you understand this process? I went a bit fast, but the idea is to use a function. So you have a sequence of numbers, you make a function out of it, and you try to apply the Laplace transform for this function. Okay? Okay. So I think I've already run out of time and 5 minutes have passed more. So just some closing remarks. So thank you for coming here, and I hope my talks were useful to you. Okay? And they will be. I am hoping that they will be useful when you are giving your own courses. Okay. If you have any doubts, you can just send me an email, and I'll try to reply. Okay. Thanks.